Thank you very much. Thank you for the invitation. It's always a pleasure to come back here. So I will talk about singularities of hypersurfaces. In fact, one of the oldest hypersurfaces that there is, the theta divisor of smooth projective curves. And it's usually very rare in algebraic geometry that you understand everything about singularities of a hypersurface. But in this case, for generic projective curves, I will show that we can understand almost everything about the local structure of the theta divisor. This project started with a question of Schnell and Young. They worked on the hyperelliptic curves, and they showed that they constructed a log resolution of the hyperelliptic theta divisor. And they posed the question whether the same type of construction, namely blowing up all the deeper Brillouin-Noether loci, would provide a log resolution of the generic theta divisor. And we will see that this is a corollary of the main result. So let me start with very basic things to introduce the subject. The theta function, what is the theta function? So it's a function on CG times the space of square matrices, G by G, symmetric and positive definite. The imaginary part is positive definite. To the complex numbers, defined as follows. So if U is a vector in CG and Z is a matrix, then we have the following: summation over all integral vectors M e to the 2 pi I transpose of M times U inner product plus 1/2 mt Zm. So it's a classical function. One shows that this is holomorphic. And it satisfies quasi-periodicity. So for that, let me introduce the following notation. If EI are the columns of the matrix omega formed by taking the identity matrix G by G and adjoining the matrix Z, then for I between 1 and G, we have the following periodicity: theta of U plus E J Z is theta of UZ, and theta of U plus E G plus J Z is E to the minus 2 pi I Uj ZJJ. That's the element on the diagonal of Z. So that's a classical object. And this quasi-periodicity means the following, gives you the following. So if Z is fixed, then the divisor of theta, the zero locus, which is denoted by this bold theta, is well defined in the quotient of CG by the lattice spanned by the EJs. So coming to the case of curves, if C is a compact Riemann surface, then we get to that situation. So let's say G is the genus now. Then we get to that situation as follows. We take omega to be a matrix of periods. So what does this mean? So the gamma j's are a basis of the first homology group. Of C. And, homology group. And we choose a special basis. We can always choose that special basis such that the matrix of intersection of the cycles is 0, the identity minus the identity 0 matrix. We can always choose that such a basis. And we can also choose these holomorphic differentials. So these form a basis of the holomorphic differentials. Then omega can be written as starting with the identity, and the rest will be denoted by z as above, and z will be as above. So the previous construction gives you a theta divisor associated to the curve. Theta C, well defined on the Jacobian of C. So that is so the dual of the space of holomorphic differentials modulo the first homology. So that's the theta divisor of a curve. I can state the theorem now. So if C is generic, in its fixed genus, then the theta divisor, the theta function, so we have Z fixed now, yeah? The theta function is locally at every point on its zero locus equal to its first non-zero Taylor term times a holomorphic unit up to a holomorphic local change of coordinates. This is a way to phrase the theorem in this classical terminology, but this is equivalent to something that we can do. We can phrase it in algebraic terms. So this is equivalent to the following. If C is generic, then at every point x on the Jacobian of C, the theta divisor is equivalent as an embedded analytic germ, complex analytic germ, with its tangent cone. At that point. What is what? Thanks. So let me spell out in a diagram what this means. So we have the Jacobian. We have a point on the Jacobian, it lies on the theta divisor, and there exists an isomorphism, excuse me. This is an isomorphism as complex analytic germ this is a smooth space, yeah? So with the tangent to the tangent space, the origin on the tangent space is H1, which induces an isomorphism of complex analytic germs between the theta divisor and the tangent cone at that point. So, and we know a lot of things about the tangent cone. So here I'll begin by revising a bit of the classical theory for theta divisor and Brill-Noether loci and tangent cones. So one has the Brill-Noether loci. WRD. So these are the isomorphism classes of degree D line bundles on the curve that have strictly more than R linearly independent sections, global sections. That's the classical notation, and in this classical notation, oops, this is running away. And this classical notation, peak 0 is the Jacobian. They're all isomorphic. Via translations by divisors of degree D. And under this translation, we have that the theta divisor is the image. So it's isomorphic with W0 G minus 1. So when the degree is G minus 1, then this Brill-Noether locus is the same as the, up to translation is the same as the Jacobian, as the theta divisor on the Jacobian, sorry. and Kempf. He showed that for every curve, in fact, it doesn't have to be generic, the tangent cone on the theta divisor, so I'll view this now as W0 G minus 1, is given by the determinant of the matrix of linear forms on H1 OC associated to the Petri map. And the Petri map is the following. Take H0 on L, multiply with H0 of omega C L inverse, it goes to H0 of omega C. So this is the dual of the space here. How do you get a matrix of linear forms on this space? Well, you fix bases here, and for each I and j, you get an element here that is in the dual of this space. So you can view this map either as a linear map like this or as a matrix of linear forms on H1 of OC. And then you take the determinant of that. And that is the tangent cone. So in particular, this completely determines the local structure of the generic theta divisor. And we know lots of things about singularities of generic determinantal variety, so we can transport all those things to the generic theta divisor. Let me also say, sorry, I didn't make the, I have to mention the following. For the generic theta divisor, so for if C is generic, then pi L is injective. So I should have made this comment before the previous comment. So this being injective as a linear map is equivalent to the matrix of linear forms associated to it to be generic. In other words, is the matrix of xij's, where xij's are independent variables. So there we know a lot about the singularities of the determinant of such matrices. So equivalently, the associative matrix is generic. This theorem can also be generalized to other Brill-Noether loci. So let me mention the generalization. So I stated it in this classical language, but you can just work over an algebraically closed field of characteristic 0. That's one of the generalizations. Instead of complex analytic germs, you can use embedded étale germs. That's also one of the generalizations. And instead of the theta divisor, you have the same statement, but for Brill-Noether loci there. So the local structure, if C is generic, the local structure is given by the tangent cone. Genericity of the curve, you can replace it with injectivity of the Petri map. That's one of the generalizations. And in fact, a higher rank and twisted version of it also holds. So let me let me introduce the setup for the generalization and write down the most general theorem in this direction. So C as genus G, smooth projective curve over an algebraically closed field of characteristic 0. F is a fixed vector bundle on C. M and D is the moduli space of stable vector bundles on C of rank n degree D. The analog of the Brill-Noether loci and this twisted setup, I'll call them VK. So these are the vector bundles such that H0 of E tensor F is greater or equal than K. So they have a natural closed subscheme structure, just like the Brill-Noether loci have. And then there's the analog of the Petri map. By star here, I mean the dual of these bundles. And let me denote the dimension here by L and the dimension here L prime. And again, one has that if this is injective, then the associated map of linear forms on H1 of this is a generic matrix. It doesn't have to be rectangular. It doesn't have to be square anymore. It's going to be rectangular in general, just like for other Brill-Noether loci. And then the theorem. So we replace the genericity of the curve with the injectivity of the Brill-Noether of the Petri map. So assume the Petri map is injective. Then there exists an isomorphism of étale germs between the moduli space locally at E and the tangent space there, so this is also smooth. So the origin of the tangent space, that's the tangent space, inducing an étale germ, an isomorphism of étale germs between this twisted Brill-Noether loci at E and the tangent cone That's the first part. So let me just say that this first part, I'm not sure about the embedded version of it, but clearly stated without the embedded version of it, in the formal case, it's also, this was obtained by Polishchuk earlier. I don't understand his proof well enough to say whether he holds in the embedded case as well, like here, but he might, he probably does. And then a second part of the theorem, this is already known by Kempf, by Arbarello, Griffiths, Cornalba, Griffiths and Harris in their book for n equals 1 and no twisting, and then by Polishchuk in his paper. So it's the full description of the tangent cone. So this is defined by the ideal of L minus k plus 1 minus of the matrix of linear forms associated, given by the Petri map. So the proof that I have gives all this again in one shot. So let me just say that this matrix of linear forms here is a L by L prime, or L prime by L matrix. When is this assumption satisfied? So we've seen that for generic curves, when we talk about Brillouin-Noether loci, that assumption is satisfied by the theorem of Giesecker. Teixidor also has a paper where she says that if the curve is generic and if this twist f is also generic, then this assumption is satisfied when you look at line bundles. So it does occur in some other instances as well. So as a result of this, so this is not only the formal case, it's et al. We know lots of things about this twisted Brillouin-Noether loci. And let me say what the new things are, but I will not say them in all this generality here. I'll say what the new things are for the classical Brillouin-Noether loci. So you recover this way almost all known results on singularities of classical Brillouin-Noether loci, at least in the generic case. So for C generic, and for Brillouin-Noether loci, the new results are as follows. I'm going to assume that L prime is greater or equal than L for simplicity. So does this dimension here has to be bigger than that? If that's not the case, use Serre duality and you get back to a situation where this is satisfied. So that's just for convenience to state things. By the way, how do we get all these results? You know them for varieties given by minors of the generic matrices by various people, and therefore you can translate them here. The local Bernstein-Salto polynomial of W0D at L is known, so it's a very explicit expression. Secondly, blowing up peak D at the following Brill-Noether loci in that order. So you first blow up this, and then the strict transform on the next, and so on, produces a log resolution of WRD, in particular for theta divisors of generic curves. This stratification of WRD, so this stratification by deeper Brill-Noether loci, is Whitney. And moreover, we have explicit local Euler obstructions. I will not write the formulas anymore, but you can write them down. Yeah, so these answer 3 questions by Schnell and Young, so that was the motivation. In fact, they posed this question only for the generic theta divisors. And this is more general. Also, there are versions of this for those twisted Brill-Noether loci, but I'll just state them only for WRDs. What else do we know? We know that the topological zeta function of WRG minus 1 is, we have an explicit formula for this. So topological zeta function is a specialization of the motivic zeta function. There's the monodromy conjecture, which says that the poles of the motivic zeta function of a hypersurface or topological zeta function, they should give you roots of the B function, or e to the 2 pi I should give you eigenvalues of the monodromy. So the stronger version now holds if we look at the intersection of these 2 cases here. So the strong monodromy conjecture of Vigusa, Denef, and Lozer and that's the theta divisor. So the monodromy conjecture is true for the theta divisor of generic curves. We have formulas for minimal log discrepancies. Multiplier ideals, Hodge ideals. There's lots of things that we know about generic determinantal varieties that we can transport directly here. I will not write any of these down. Another result that I would like to mention, this was known before by Zhixian Zhu, a student of Mircea Mustață. So she showed that for generic curves, she computed the low canonical threshold for Brill-Noether loci of generic curves. There's a very specific formula for that. And she remarked in that paper that it looks exactly like the one for generic determinantal varieties of the appropriate size. But her proof could not explain that. She used jets and arcs. Whether, so now you see clearly that we can recover the result directly because the local architecture for generic determinant of varieties was known before. So this explains now our observation. All right. So I have some time to tell you about the proof of this result, of this one here. So the proof splits, it has two distinct parts. First one proves the embedded, so the part A, but for the embedded formal case. And as I said, without the embedded part, this is something that Polishchuk has done before with some different techniques that I don't fully understand. But then one needs to bring it from the formal case to the holomorphic case or the et al. Case. And for that, one uses some embedded version of a very specific Artin approximation. Specific in the sense that you're dealing with tangent cones. Tangent cones are specific there and the embedded version of Artin approximation. So then you get from the formal statement to the et al. Or the analytic statement. I will explain this part here. And for this, I had developed with my co-authors some time ago a more general theory. It's called deformation theory with cohomology constraints. So what do we want to do? We want to do the following. For any moduli space of some objects which have a cohomology theory, we want to understand the cohomology jump loci as closed subschemes locally. That's exactly what the embedded formal version of part A would give. Now, classical deformation theory is dealt with Deligne's principle, which says that every deformation problem over a field of characteristic 0 can be understood in terms of differential graded Lie algebra. And any two equivalent DGLAs give the same answer to that deformation problem. This has been enhanced by Fukaya, Kontsevich, and others so the deformation theory has been enhanced to work with L-infinity algebras. The problem with DGLAs is that usually they're infinite dimensional, whereas if you pass to the cohomology of that complex, of that DGLA, that's usually finite dimensional. So you gain finite dimensionality, but at the expense of introducing other higher order multiplication operators than just the Lie bracket. What I did with my co-authors is to enhance this with cohomology constraints. And obviously, we have a cohomology constraint problem here. Yeah? The constraint is that the sections of the thing that you deform after some twist, that fixed twist have to be bounded below the number of sections. So what is this theory? So we have a moduli M, and here we have some cohomology jump loci. So VIK will mean the points parametrizing the set parameterizing those points in the moduli where hi has dimension greater or equal than k. And in all situations of interest, these are closed subschemes. And we have a point here. So we want to understand all formal germs at once of M and Wik, so in the embedded situation with their inclusions and so on, at E. That's the deformation problem with cohomology constraints. Obviously, if you put k equals 0 here, then that's just M. So M is just one of these guys. And the answer, so if you just want to understand M locally at E, there's deformation theory. You have a DGLA according to Deligne. And that gives you the answer. And we said that to understand further the rest, all you need, well, you get that by a certain DGL module over C. So the version over with DGLA pairs, this was done together with Wang in 2015. And then, of course, we also wanted to do this in the fancier but better, more flexible way in terms of L-infinity algebras. So the classical answer for local structure of M at E is given by the cohomology of C, but as an L-infinity algebra. And now we also need the cohomology of M. And this is going to be as an L-infinity module. If you start the DGLA pair like here, then taking their cohomologies, you naturally have operations, L-infinity algebra and L-infinity module structures on their cohomologies. Okay, so let me just say a bit what L-infinity algebra means. So an L-infinity algebra is that there are some higher order multiplication maps now. So we have higher order multiplication maps that are graded of degree 2 minus n. And the first one, in general, that should be a differential, but because you work with cohomology, in this case, the differential is 0. The second one is really the induced, so you have a Lie bracket here, and that induces a pairing here. But now there could be many others, possibly infinitely many others higher order operations. And the L-infinity module structure means that there are higher order multiplication maps from C on M. So Mn are these higher order multiplication maps. Also graded degree 2 minus n. And again, the first one should be a differential, but again, because we're in the cohomology here, the differential has gone away. That's one of the advantages of working with cohomology. But then and M2 is the one induced from the usual multiplication here, coming from the DGL module structure. Of course, there are axioms here to be obeyed, just like there are axioms for the Lie brackets here and so on, but I will not write those down. So what does it mean that this answers the problem? So you want to understand the formal germ at E of this cohomology jump loci. And you can view this as a functor. So when you have moduli spaces, you don't need to work with them as a functors, but the problem for deformation is well defined even if you don't have moduli spaces. Deformations don't need a functor. So then the functor is on finite type Artinian rings over, let's say, in our case, the field K of characteristic 0. So you take an Artinian local ring, A, And you want to understand what this does. And this is the solution of the problem in terms of the L infinity pair. We look at omegas in H1 of C times the maximal ideal of A. I'm going to put C here, but you can work over characteristic 0. Whatever, K. And then this is the Maurer-Cartan equation, but in the L infinity setup. That has to be 0. And secondly, I'm going to write here a complex of A modules. So those are the vector spaces, and here's the differential. So this, because this is a Maurer-Cartan element here, we can show that this is a differential on this complex. So this is a complex of A modules. And what you do, you take something called the cohomology jump ideals of a complex of A modules, and you set the condition of that being 0. And then there's also some action that puts some omega on the same footing, so some equivalence action. You have to mode out by H0C tensor MA. What is the cohomology jump ideal of a complex of A modules? So this has to be bounded above and have finite cohomology. And the definition I'll give in general. So if you have a complex of modules of a Noetherian ring that's bounded above with finitely generated cohomology, then what you do first, you take a free resolution of that complex. And then in that free resolution, you look at di minus 1 direct sum di of f. Yeah, so the two matrices, you put them together and you form a big matrix from the differentials of that free resolution. And then you take the ideal of minors of size rank of Fi minus k plus 1. And that's the cohomology jump ideal. So it's a generalization to complexes of the classical notion of fitting ideals. If you let k equal 0, so you just have the moduli space, then there's no ideal here, and that's the answer. The Maurer-Cartan equation is the answer given by Fukaya, Kontsevich, and so on to the deformation problem. Now, what is this pair in the case of deformations with cohomology constraints of a vector bundle on a smooth projective variety? So this pair is just the cohomology of V, of the endomorphisms of V, and so I'm going to do the twisted by F cohomology jump loci just like there. So then this is this pair. There's some natural L infinity operations, and that's the pair. Now, in the case of a curve, a lot of things simplify. First of all, even before the case of the curve, if you're working with stable vector bundles, which is what we do, there's nothing to mode out anymore. so you can get rid of the modding out. So that's one simplification. In the case of a curve, for dimension reasons, there are no higher order multiplications for the L infinity algebras, for dimensional reasons. That also tells you in a very fancy way that the moduli space is smooth. So there are no conditions anymore. So if X is dimension 1, this is 0 for n greater or equal than 2, and only the following multiplication maps matter. On the module side. If n equals 1 here, then this is actually the Petri map. The higher ones you don't really know, you don't have control of them, but you know at least that you get the Petri map. So to put these observations together, then the first observation here tells you that the formal germ is smooth, so it's isomorphic with the tangent space there. And this is classical deformation theory. You well knew that. That's the tangent space. And now, if we consider the twisted Brillouin-Odar loci that we want, then now I have actually schemes. So instead of having a functor on Artinian rings, I can actually work with the formal germs. So this is the formalized spectrum of a power series ring, and this is a vector space. So now I have to take the zero locus of an ideal, that's the ideal condition given here. I take its completion at the origin. So what ideal do I have here? I have J0k of a complex of modules over the formal power series in the dual of this vector space. So and what complex of modules do I have here? That's given by these maps here. Now, so there's the complex, so the differential, so there's only, what complex is here is the following. It's H0 E F times S. This is S, the polynomial, the formal power series ring. H1 and here I have the map. So this map here is given by so I prefer to use this map now here. What is the point? We are assuming now that we're in the genetic case. So I know that so this is a matrix of formal power series. These are the homogeneous terms of those formal power series. And the linear part of that is given by the matrix associated to the Petri map. Now we know that that's generic because that's one of the assumptions on injectivity of the Petri map. So if you have a matrix of formal power series such that the linear part of each entry forms generic matrices, then you can find a formal change of variables such that the whole thing is generic, determinantal. And then applying this minors thing here, you get the result. So sorry for going overboard.
Okay, thank you.